Now the question is whether for this situation also the determinant of the matrix is nothing but the area of the rhombus, that is, since we have started with a unit square space, whether now the area of the rhombus is 3 or not. Just to give you an insight into things, first we would find the area using trigonometry, and second we would find the area using vector cross product. Now this is the transformation matrix that we used to transform the square space into a parallelogram, and you can see that this has only one shear term, or the term that brings about a rotation or distortion, and the determinant of this transformation matrix happens to be 4, which is nothing but the area of parallelogram, because earlier we started with a square space of unit area. Now you have a parallelogram whose area is nothing but 4, and once again the fact that the scale by which the area gets amplified is nothing but the determinant of the matrix. Now if I were to introduce two shear terms, that is both for x and y, then the obvious expectation is that the square space gets transformed into a rhombus, because you see that the column which is transforming the x vector is having a shear term, and the column 2 which transforms the y vector is also having a shear term. So therefore when this transformation matrix operates on the x vector, you get 2, 1. When this transformation matrix operates on y vector, you get this, and therefore a square space gets transformed into a rhombus. Now the question is whether for this situation also the determinant of the matrix is nothing but the area of the rhombus, that is, since we have started with a unit square space, whether now the area of the rhombus is 3 or not. Now that can be checked. Of course, let's first find the determinant of the transformation matrix, which is 4 minus 1, which is 3, and you can also see that the area of the rhombus formed is also 3, and let's do that in two ways just to give you an insight into things. First we would find the area using trigonometry, and second we would find the area using vector cross product, and then interpret both the results, and we would also try and introduce the concept of eigenvector and eigenvalue, which becomes more appropriate in this transformation. So let's proceed. Now we computed the determinant of the transformation matrix to be 3, and it has to be verified that the same value has to be that of the area of the rhombus shown. Now if you looked at the triangle OAB, it is easy to compute the area of triangle. It is nothing but half into OA into OB into sine of angle between those two sides. From the figure, it is clear that the angle between them is 90 minus 2 theta. So therefore, since each side is equal to root 5, the area of the triangle is half into the product of those two sides multiplied by sine of angle between those two sides, which is 90 minus 2 theta. Of course, this is from the elementary formula for area of a triangle. When I double this, I will get the area of the rhombus, because rhombus can be split into two identical triangles, you can see in the figure. Now sine of 90 minus 2 theta is nothing but cos 2 theta, and root 5 into root 5 is 5. This 2 would get eliminated, 5 cos 2 theta. Now cos 2 theta is nothing but cos square theta minus sine square theta. From the figure, cos theta is nothing but 2 by root 5, and sine theta is nothing but 1 by root 5. When I plug in those values, I will get this. It is 4 minus 1 by 5 into 5, which turns out to be 3. Well verified. Now let's also incidentally look at the coordinates of the vectors, and also the diagonal lengths and their slopes, so that the discussion could be extended to the idea of eigenvalues and eigenvectors subsequently. First, of course, we will find the area using vector method, then we'll come back to this. We also know from the elementary high school mathematics that rhombus area is nothing but product of its diagonals, rather half into product of its diagonals. Now, length of the short diagonal, you can clearly see the coordinates have been indicated by distance formula. It is root of 1 square plus 1 square. And again, applying the distance formula for the longer diagonal, you can see that its length is square root of 3 square plus 3 square. Root of 1 square plus 1 square is nothing but root 2, and root of 3 square plus 3 square is nothing but 3 into root 2, and area is nothing but the product of diagonals by 2, which again turns out to be 3. So therefore, the determinant of the transformation matrix is nothing but the ratio of the two areas, the area of the rhombus by the area of unit square space, which is 3, which is got by these two methods. Now, the second method I am going to attempt is the vector method, and then we will come to the definition and interpretation of eigenvalues and eigenvectors. But remember that the diagonals have length root 2 and root 2 into 3. These are two diagonals, and you can also incidentally verify that slope of the short diagonal is nothing but tan 135, that is minus 1, and slope of the long diagonal is 1, that is it makes an angle 45 degree to the x-axis, whereas the short diagonal makes an angle 135 degree with respect to x-axis. Now let's try and interpret them a little later, but for now let's move on with the vector method. Now, having found the area using basic trigonometry and coordinate geometry, now let's move on to find the area using vectors. Now you can clearly see that the vector product of two vectors would give you the area of the rhombus or the parallelogram in general. Now, what are the two vectors in question? That is vector number 1, 2, 1, 0, that is the x component being 2, the y component being 1, and the z component being 0, and the second vector in question has got 1 as x component, 2 as y component, 0 as k component. Now, what is to be emphasized here is that area is a vector quantity and whose direction is given by a normal unit vector, that is a vector perpendicular to the area. Now, the direction of the area that we get here, if you are interested only in magnitude, it doesn't matter, but if you are interested in the direction of area, then what happens is, if the transformed x vector occupies the third row and transformed y vector occupies second row, then you get a negative value. That means the normal of the area is into the plane, and for this particular arrangement, the normal of the area is out of the plane. Now, this is how you determine the cross product. You find the determinant of this matrix, and you can clearly see that it is done as follows. It is I multiplied by 1 into 0 and 2 into 0, you get 0, and then minus j, you get 2 into 0, 1 into 0, you will get 0. Because these are two planar vectors, obviously you will get a resultant vector which is perpendicular to these two vectors, which is of course a vector along z axis, because these two are in the xy plane, and the last vector is plus k into 2 into 2, 1 minus 1, that is you will get k into 2 into 2 minus 1 into 1. So if you seek the magnitude of that vector, which is nothing but the area, which is magnitude of 3k is 3, and again you go to corroborate the fact that the increase or the amplification factor for area is 3, which is nothing but the determinant of the scaling matrix. Now, we'll continue the discussion and see what are the eigenvalues and eigenvectors of the transformation matrix and how they have to be interpreted in case of this transformation. So let's proceed.